Hello everyone, I am Biplav Bhattacharya and I welcome you all in this course Introduction to Sequence Stratigraphy, and in this particular class we are going to discuss on this particular topic, relative versus absolute ages. So whenever we talk about stratigraphy, we have to deal with the time, geological time, and in stratigraphy we try to arrange the rock succession, rock units and the corresponding events in chronological order, that means in order of time from older to the younger. So, whenever we deal with that kind of problem, a succession which is having some sort of appearances in terms of time, we have to determine the exact age of formation or deposition of that particular rock body, or we have to understand what is the time of that particular event, which may not be a deposition of a rock, maybe some other event like a faulting, like a folding, like a thrusting. So, all these events and processes, geological processes and their corresponding products in the form of some litho units, they need to be dated, that means their age has to be understood in order to get a stratigraphic succession. So, in this particular class we will discuss about how we can determine the age of such stratigraphic succession, what do we mean by determining the age of stratigraphic succession, and what is the concept of relative versus absolute ages. This discussion is distributed in two classes. First part we will discuss in this particular class and the next part will be in the next class. So, in stratigraphy commonly the term chron is used equivalent to age, and very commonly we do chronostratigraphy correlation, where we try to match up the stratigraphic units on the basis of time equivalence. So, we try to determine different rock units and we try to match them in terms of their relative age similarities or their age correspondence. So, this kind of activity is the backbone of any stratigraphic work, any stratigraphic succession. So, there can be several methods which you can apply, which are already established to determine this time stratigraphic correlation, chronostratigraphic correlation, where straightway we can apply two dominant methods. One, where straightway we use some biological tool, for example, certain fossils which can denote a particular age, which corresponds to a particular age, and that can be very effectively used for biostratigraphy and also for chronostratigraphy. And the second one is the physical or some chemical tool, chemical components which are present within the rock succession, and that can be used for dating the rock, sometime in a direct method, we call it as the absolute age determination method, or it can be an indirect method where we get a relative age. That means, in those cases we do not get the actual age, but we try to arrange the rocks in order of their relative older or younger occurrences. We call it as the relative age dating method. So, in biochronology, that means when we are using the biological tool, the fossils as the dominant tool for this correlation and the dating purpose, in that particular process we try to calibrate the geological time according to the irreversible process of evolution in the organic continuum. If we look into the overall earth history, gradually the life form has evolved from very small organisms to more complex and more evolved forms, and different organisms, they have appeared at different times and they have also disappeared, they got extinct in the geological time. So, if we can have a clear idea about that appearance and disappearance of these different fossils, different organisms through geological time, very effectively we can use that for the correlation or age determination of stratigraphic succession. So, in biochronology we try to correlate and date the stratigraphic succession by using the paleontologic features or some major paleontologic events. Examples, some new form has appeared, or maybe some forms which were existing, they have disappeared, or maybe one form has changed into a new form, into an offspring which is significantly different, and those events are widespread, that means they are occurring across the globe or affecting a major part of the globe, which can be easily identifiable, which can be easily demarcated in the rock succession, and they can be incurred within a very short period of geological time. So, when this kind of events occurs within a very short period of geological time, say for example within 100 years time or maybe 1000 years time, which is actually a very short time period in terms of overall geological time scale. So, we call that kind of biological event as a datum event. So, it can be the first appearance datum, where certain organisms has appeared for the first time on the earth, or it may be the last appearance datum, that is the extinction of certain organisms within a particular succession in a particular area, and in that way we can identify the range of occurrence of the organisms in terms of FAD and LAD, that is the first appearance datum and last appearance datum, and depending on what kind of rocks are there where this kind of FAD and LAD are present, we can get an age, we can determine the age of that particular rock succession. So, in some cases it can give us a direct age, in some cases it can give us a relative age. So, when we are talking about this relative age dating, we should have a clear idea about what is relative age dating. However, we will discuss about relative age dating in the next class, not in this particular class. So, we can determine the age of a particular rock, that means when that particular rock has formed through certain methods. A major type, a dominant type of the methods is radiometric age dating, where certain radionuclides, certain elements which have this radiometric property can be used for determining the age, and there in those cases we get the absolute age, that is in terms of number we get the age. But many cases we do not get that absolute age, or we do not get a favorable mineral or a favorable condition within a rock where we can apply this absolute age dating method, which is very true for most of the sedimentary rocks. So, in those cases we have to go for a relative age dating, which used to be there in practice before this absolute dating of rock was developed. So, at that time before this 20th century, geologists they had to rely on the relative age dating methods. So, in this relative dating method, what we do, we try to understand using this basic stratigraphic principle, the fundamental stratigraphic principle, we try to arrange the rocks from oldest to the youngest, and we place them in their relative order of appearances. This method in certain cases can be useful, but definitely if we get a particular age, an absolute age in terms of a number, that is always more useful, more helpful in determining the absolute stratigraphic arrangement of the rock bodies. So, for determining the relative ages, there are certain principles we follow that we will discuss in detail in the next class, and also for dating the rock in terms of absolute age, there are certain methods which we will discuss in this particular class. So, when we talk about the absolute age determination, the most common way, the most common tool or methodology is the radiometric dating. So, in radiometric dating, what we do is we try to find out certain elements which is present within a mineral within the rock, and that element have some isotopes which is basically a radiogenic isotope. So, what happens? It is an parent isotope. So, from that parent isotope we get certain radiometric decay, and due to that decay we get a daughter isotope. So, at any point of time we can determine the ratio of the parent isotope versus the daughter isotope. For certain elements, that ratio has certain standard time period which we commonly call as the half-life period. So, based on that we can use them for the determination of or the measurement of the age of the rock. So, very commonly for absolute age determination process we use two major decay process, or there are two major decay processes which are directly used for absolute age determination through radiometric dating method. So, number one is called as alpha decay and number two is beta decay. So, what is alpha decay? In case of alpha decay, from a parent isotope, say this is the parent isotope, from there we get a daughter isotope, and along with that an alpha particle is emitted. What is this alpha particle? It is nothing but an helium ion, helium plus 2. So, this helium plus 2 is removed, emitted from this parent isotope, and as a result we get a new daughter isotope. A very common example is 147 Sm, which leads to 143 Nd with emission of one alpha particle. So, this Nd 143 Nd, this is the daughter isotope, 147 Sm, this is the parent isotope. So, at any given time what we can get is a ratio between this daughter versus parent isotope, a ratio between Nd by Sm within the mineral. Now, what is a beta decay? This is nothing but emission of an electron. So, again in this case a parent isotope, it decays to a daughter isotope, and along with that it emits one beta particle which is nothing but an electron. So, most common example for beta decay is rubidium. So, rubidium 87, this is the parent isotope which decays to strontium, which is again 87 with one beta particle in an electron. So, in this case rubidium is the parent isotope, strontium is the daughter isotope, and at any point of time we can get a ratio of strontium versus rubidium within minerals. So, for certain elements which are radiogenic, they maintain a particular ratio in terms of their rate of decay, because they decay at a particular constant rate, and so after certain time we can get a particular ratio if we know how much is the parent isotope was present. So, within a particular mineral we can get this ratio, and from that ratio we can get the half life, we know the half life, and using that half life we can determine the age of that particular mineral when it was formed. So, what are required for this? The rate of decay should be known to us. For example, rubidium to strontium, what is the rate of decay? That should be known to us, and fortunately at this point of time for almost all the common radiometric dating methods, we know what are the rate of decay for common decay processes. For example, uranium lead, for example SMND, for example potassium argon, these are very common. For example, carbon isotope dating. So, for all this type of radiometric decay we know the rate of decay. The second point which is also required, we should know the proportion of different isotopes present within the mineral when the mineral formed. This can be calculated as we know the composition of the mineral, the chemical formula of the mineral, and from there very easily we can understand how much that isotope was originally present in that particular mineral at the time of its formation. And what we have to know, the third one, the proportions of different isotopes present today, and this we can directly measure. So, we can calculate the parent isotopes, we can measure the daughter isotopes, so the ratio can be calculated, and since we know the rate of decay, using that straightway we can get idea about the age. So, for this purpose, for determination of the age, some very traditional common equations are used. So, commonly the first equation that we commonly use is N, which is the number of daughter atoms or daughter isotopes after a period of time t. So, this N is equal to N0, which is the number of parent isotopes or parent atoms at the beginning of this process, and then we get this L, which is the rate of decay, or it is also called as the decay constant. So, this rate of decay is fixed for a particular pair of atoms, a particular pair of daughter and parent atoms. So, in this equation we can measure N, we can assume or calculate N0, we know the L value. So, what we can calculate is the time. So, how much time is involved to fulfill this equation. So, within this equation what we are getting is this particular time, which can be represented in terms of this equation. This is just the another way we write this equation. So, here 1 by L, which is the decay constant or the rate of decay, into log natural the parent isotope by daughter isotope plus 1. So, using this kind of basic formula, we can very easily identify or calculate the absolute age, the time duration involved in a particular radiometric process, and that can be very effectively used for the determination of absolute age of the rock. So, it is normally assumed that when a mineral is crystallizing out of magma and it is forming an igneous rock, at that particular moment a radiometric parent isotope is getting trapped within the mineral, and once it is trapped, that radiometric atom will start decaying from that particular moment. So, we can also assume that only the parent isotope is present when a mineral is precipitated chemically in a sediment or it is formed in the solid state recrystallization in a metamorphic rock. So, it can be within the igneous rock from a magma when it is crystallizing, maybe some diagenetic changes, some chemical precipitation of mineral within a sedimentary realm, or recrystallization in a metamorphic domain. So, whatever may be the case, whenever a mineral is forming, there the parent isotope is trapped. So, that is the first assumption, and once it is trapped, it starts decaying, and at that point when it is trapped, at that very initial moment, what we consider is there is not a single daughter atom or not a single daughter isotope. All the isotopes of that particular element are parent isotope. So, from that point, as it is trapped and it starts decaying, the radiometric clock starts as the mineral is formed. So, basically when we are calculating the age using these formulae, what we are getting over here is that particular time of trapping, the time of trapping of the element within the mineral. So, that may be the age of formation of an igneous rock, within that the mineral is trapped, or it may be the age of diagenesis or chemical precipitation within a sedimentary domain, or it can be the metamorphic process. So, we have to look at the mineral type, which mineral we are looking at. For example, if it is a say in a granite body, so there it can be a zircon trapped within a granite body. So, it is the age of magma crystallization. Maybe we are looking at a glauconite. So, glauconite forms in a sedimentary rock in a sandstone during diagenesis, and within glauconite we can get potassium, radiometric potassium changing into argon. So, that particular age that we will get is the age of diagenesis, or maybe we are getting some metamorphic mineral and there also we are getting some sort of isotopes. Say for example, we are getting some chlorite or some muscovite and there we are getting some potassium within that muscovite. That will give us the age of metamorphism, the formation of the mineral during the metamorphic changes. So, there are several tools available to us in terms of the type of parent daughter pairs, which can be very effectively used for the determination of age of rock bodies. For example, uranium-238, which is a radioactive element that decays to lead-206 and it decays through a time period of 4.5 billion years. And normally the material that can be used over here are zircon, monazite, sphene, commonly trapped within igneous rock or maybe some metamorphic rocks. So, when the half life is 4.5 billion years, that means the entire age of the earth can be covered. So, any rock type starting from Archean to the recent, any type of rock or mineral can be dated using this particular method. Similarly, uranium-235 decaying to lead-207, this is the daughter element. So, in this case the time involved is 704 million years, the half life. So, again it is a very large half life and it can be very effectively used for dating older rocks. Again the materials are certain minerals present commonly within igneous and metamorphic rocks. Third one, rubidium-87 decaying to strontium-87, RBSR method. Here again you can see the half life is 48.8 billion years. So, this is a very large half life, and so rubidium strontium can be very effectively used for very old rocks, for dating of very old rocks, even the Archean rocks. So, in this case we can apply this to any rock forming minerals, commonly potassium bearing minerals like feldspar, like muscovite, because there potassium is replaced by rubidium. So, they can form in metamorphic rocks or in igneous rocks. Next one, potassium 40 leading to argon 40, potassium argon method. Again, in this case you can see the half life is very large, 1.25 billion. So, again effectively it can be used for almost all ages of rocks. We can determine any geological age starting from Archean to the recent, and again in this case the potassium bearing rock forming minerals and also some volcanic rocks where we can get some plagioclase feldspar. So, within this kind of rocks straight away we can apply the potassium argon methods. Next one, another very common method is the samarium neodymium method. So, samarium 147, neodymium 143 having half life of 106 billion years, again a very large half life and can be used in any kind of rock, basically igneous and metamorphic rocks, but they occur in very small concentrations. And the last one, the carbon 14 changing into nitrogen 14. There is a radiometric carbon changing into nitrogen 14. So, the amount of half life involved is 5730 years. So, the half life is significantly small in this case, and that is why the carbon 14 method is commonly used for determination of age of recent sediments, maximum up to the Cenozoics. Beyond that, we cannot get good result using carbon 14. And for this purpose, any kind of organic material which is present in the rock, which is preserved in the rock, including recent materials like wood, charcoal, coal, there we can apply this carbon 14 method. So, these are some of the very commonly used radiometric dating methods which we can very effectively apply for determination of age of the rock succession. But as you can see over here in this particular list, most of the methods are actually applicable or useful for igneous or metamorphic rocks, not for sedimentary rocks. Why? Because as the principle says, these elements are trapped within the mineral during the formation of the mineral. But during its sedimentary process, normal clastic sedimentary process, minerals are not formed because the earlier rocks, they get eroded, transported, the clasts are transported and finally they get deposited. So, everything is physical process, and during this inter-physical process, no new mineral is formed. So, there is no chance of these isotopes getting trapped within the minerals. So, for example, we are getting a sandstone. So, within that sandstone maybe a potash feldspar is present and that feldspar bears some radiometric potassium, potassium 40. So, we can date that potassium 40 using potassium argon method, but the date that we will get, the age that we will get is the age of trapping of that particular potassium in that feldspar. So, that is the age of the crystallization from magma, not the age of sedimentation. So, none of these processes, none of these techniques can be effectively used for sedimentary rocks except few. For example, potassium argon method can be used for a particular mineral called as glauconite, which is a diagenetic mineral and very commonly it forms in sandstone, sometimes in mudstone as well during diagenesis through chemical precipitation. So, when chemical precipitation of a new mineral is going on in the diagenetic realm, there we have a chance that again some radiometric element like potassium 40 may get trapped, and so within glauconite, which is a potassium bearing mineral, we can get some radiometric potassium trapped within that, and from there on we can get some daughter argon isotopes. That potassium argon ratio will give us the age of diagenesis, and since diagenesis is a very common process just after the physical sedimentary process, so we can consider the age of diagenesis as very close to the age of sedimentation. So, these dating methods are principally used for determining the age of formation of the igneous rocks. In many cases, the age of formation of the volcanic rocks that occur within the sedimentary strata. But apart from this last example that I have given to you, this glauconite where we can apply potassium argon, or maybe some other clay minerals like illite where again we can apply this method, apart from those very rare cases, we cannot apply the normal radiometric edge dating method for sedimentary strata. So, it remains as a big question that then what is the use, because in stratigraphic succession most of the rock units are sedimentary rocks. So, that particular component we will discuss in the next class, where we try to determine the age of sedimentary rocks using some different tools, and there comes the concept of relative age dating method. So, in this particular class we can summarize that we discussed about the concept of age, the relative age and the absolute age, and we have tried to understand what are the methods of absolute age dating method, which is very much equivalent to the radiometric age dating method. So, under that we have tried to learn that what are the basic principles of radiometric age dating and what are the common methods used. Definitely that list that I have shown to you in this particular class, that is not all inclusive. There are many other radiometric age dating methods. There are many such parent daughter isotope pairs are there, which are also very commonly used for determining the age of the rocks. The methods depends on the type of availability of the equipment, the type of availability of the mineral which is present in that particular rock. So, these are some references which you can also go through for further detailed study on this particular topic. So, thank you everybody.